Last time we met, we did some integration, basically the easiest type of function to integrate. Let me get my pen working. The idea is the exact opposite of a derivative, right?
Mm-hmm.
What does it give you when you integrate something? When you derive something, it gives you the slope. What about the other way around? So you have something like this. Let's call this y equals x. It gives you the area, okay?
Mm-hmm.
If you see this, you're integrating this function, which is x, from x value of 0 to x value of 3. This is what it gives you. This is the area. What did we do? We did something like y equals 3x to the power of 4. Let's look at this one. Let's say we want to take the integration of this function. The power is going to go up by 1, right? It's always going to be x5. But there's a 3 here. If you were to bring down the 5, you would have a 5. But what you need there is actually a 3. So what do we multiply this by? It's something like this. You have x5. In front of this x5, you need to multiply it by something. Right now there's a 5. When you do this, you would get a 3. The question is, what do we multiply this by? And it's not that difficult. You need a 3 there, so introduce a 3. You need to get rid of this 5, so introduce a 5. This will cancel with this, and you would get a 3. Okay?
Mm-hmm.
So here you'd multiply it by 3 over 5, like that. And there's always going to be a plus c if it's an indefinite integral like this one. So that's for polynomials, which is the power is always going to go up by 1. It also works for radicals as well. Anything that you can write in that form. Let's look at a different type of a function. Let's say you have e to the power of 2x. What's the derivative of this?
Itself
Yeah? Anything else?
times 2.
Times 2, right? So that would be the final function. Now let's say you're starting down here. Let's say this is e to the power of 3x, and we're taking the antiderivative. So this is your y prime essentially. Now let's look at what y is going to be. E to the power of anything, it's always going to be itself. So there's going to be e to the power of 3x. Now, if you were to take the derivative of this, there would be a 3 component in the front. There's no 3 component here. So you need to get rid of that. If you were to take the derivative, there would be a 3 here, but there's nothing at the end. There's only a 1 here. So now what do you multiply this by? Well, you need to kill the 3. So you'd multiply it by 1 over 3. And this would cancel out with this, and you'd be left with a 1. So here it would be over 3 plus c. And that's what this thing says right here. Whatever the number up here, being multiplied with x, you need to divide it. This thing is a little bit more complicated. Ln of x, the integral. We'll do this maybe in a couple of classes, because by itself, ln of x is a pretty difficult function. Like the derivative of ln of x is 1 over x. If this is y, this is going to be y prime. This says, well, what if that is y prime? They want to go one level higher. And turns out the integral of ln of x is this. Um, how do they get that? They use a process called integral by parts. which is a little bit complicated. We'll get that later, get into it later. But that's the formula here, which is very helpful because that procedure is pretty long. And then finally, we have this b to the power of x, where this b is any constant. So let's say you have 2 to the power of x. If this is y, your derivative would be 2 to the power of x times ln of 2. Well, if that's your derivative, the integral, well, it's always going to be itself. But if you're going down, you need to multiply it. If you're going up, you need to divide it. That's what this says. So it's the exact opposite. You just think about dividing it, and I think that's gonna help us out. We'll do a bunch of practice problems. It's not terribly difficult. And there are some other trig functions. We didn't really get into this. You don't really get into this in high school here. But they are some other trig functions. Let's just keep it like that. They look completely different. It's a different type of trig function. It's derived from the original functions. These are called hyperbolic functions. We won't get too much into this because we haven't covered the basics for that. We'll start easy. Let's look at this one. So this is case number 1 up there. What would be the integral for this? Here a is -1. You can even think about it that way. Like see, e to the power of ax, a here is -1. It would be
Is
itself.
it over -1?
Yeah, that's it. So it'll be e to the power of x. So the exact same thing divided by -1. Is there going to be a plus c here?
No.
No. So that -1, I'm just going to write it in the front here. Like that. And then we're going from 0 to infinity. Okay? Like that.
Mm-hmm.
So when this happens, it's always going to be the upper bound that's going to get plugged in there. Minus, whenever there's a minus, make sure to have it open a bracket. And it's this lower bound that goes in there. Like that. Now let's look into both of these quantities on the side here. E to the power of negative infinity. Forget about the minus sign for now. E to the power of negative infinity. You can rewrite this as, I want to get rid of the negative sign. This is basically radical math. You can move it up and down, right? Makes it positive. Do you agree with this?
Mm-hmm.
Now think about this, that we're never going to get an exact value because infinity is not an exact number. But e to the power of a very large number. Now, e is a positive number, right? It's like 2.7 something. So you have this number, and you're taking an exponent, a very large exponent here, right? What is this entire thing gonna converge into? What is it gonna head towards? This number is getting larger and larger. You only have two options. It's either gonna be 0 or infinity. Where is this headed towards? A positive number with a large exponent.
Infinity.
Yeah, infinity. So you can think of this entire thing, e to the power of infinity, that is headed towards infinity, okay? Here's another interpretation of that. Let's say you have the function e power x. We know what that looks like. That's just an exponential function like this. This is the function e power x. Now when x goes to infinity, right, over here, the question is, well, what's the y value up there on that curve? What's the y value? Turns out that's infinity, right?
Mm-hmm.
So you can think of this thing, e to the power of infinity, as simply infinity. Now let's look at this one, 1 over infinity. 1 divided by a very large number. What is that going to head towards? 0 or infinity?
0.
0. So 1 over infinity is a 0. So that's what we're going to treat this as. E to the power of negative infinity is, well, this, which gives us 0. So this entire thing is negative 0. So negative 0 is a 0. So we can completely ignore this. That entire thing is exactly 0. Let's look into this one. E to the power of negative 0 is just this. E to the power of negative 0, I can rewrite that as what if I want to make the exponent positive?
1 over e to the power 0.
What is e to the power of 0?
1.
1. So that entire thing is a 1, right?
Mm-hmm.
And then let's plug this as a 1 in here. So this thing is a 1. You have a negative negative, that's going to become positive. So the entire answer is positive 1. Cool?
Mm-hmm.
Let's see what that actually means. So we just did something. What does it actually mean? So our function is e to the power of negative x, right? Which, not cheat, it looks, you can think about it. I mean, we know what e to the power of x looks like. We don't even need to cheat here. We can make a sketch. Remember, the answer was 1. We already have e to the power of x here. We can just build from this. Now think about what this transformation does. There's a negative here. Is this a reflection on the x-axis or a reflection on the y? It's one of those two. The minus sign there.
The x.
It's the y-axis. So look at this one. Let's say you have x cubed. Looks like this. If the minus sign is in the front, like this, it's a reflection on the x-axis. So it flips upside down. This becomes the mirror plane, and then it kind of flips upside down. If the minus sign is inside the function itself, by that I mean now this is going to get replaced. That is a reflection on the y-axis. If it's inside the function, it's a reflection on the y-axis. So it would look like this, okay?
Mm-hmm.
So here, it's a reflection on the y-axis. So just think of this as your mirror plane. So e to the power of negative x looks like this. Cool?
Mm-hmm.
Will it ever cross the x-axis?
No.
No. So the fact that we found a 1 here, that means that the area under the curve from 0, you see x equals 0 is here, right? To maybe infinity is there. Again, the infinity is just a theoretical concept. We won't actually reach there, but let's say infinity is there. What we found here is this area. Cool?
Mm-hmm.
The area here for e to the power negative x from 0 to infinity was exactly 1. So not too bad. These are all definite integrals, so there's never gonna be a plus c. It's like a ln of x. It looks tricky, but we have the formula right up there. What's the integral of ln of x? It's right there, right? Here. X ln of x minus x. There's not gonna be a plus c because you have bounds, okay?
Mm-hmm.
And then we're gonna plug e here, 1 here. Remember, what's ln of x? What's the inverse of ln of x? It's e to the x. e to the x looks like this. Ln of x is the inverse function, which will look like this. Where e is the natural number, 2.71 something.
Mm-hmm.
Ln of x is equivalent to log base e of x. So these two are inverse functions. So when you plug an inverse function within the main function, I can treat either one as the inverse of another. If you plug any value x in there, they cancel each other out. You would get an x. For example, let's say you were doing e times ln of 2. They're going to cancel each other out. You're just going to get a 2, okay? What should be up
Mm-hmm.
here? Ln e to the ln of 2. It should be written like this. E to the ln of 2 would be a 2, and ln of e to the 2 would be a 2 as well. They cancel each other out. So here, put the upper bound in as x, e times ln of e minus e minus, you're going to put the 1 in there. So it'll be 1 times ln of 1 minus 1. And this is another core concept here. E to the x goes through the point 0, 1, always intercepts the y-axis at 1. Whereas the inverse function ln of x always intercepts the x-axis at 1. This goes through the point 1, 0. What this means is that ln of 1 is a 0. And ln of e, remember they're inverse functions, that is going to be 1 because the power of e is here is 1. So at some x value of e here, which is again 2 point something, let's say that's 2, 2 point something would be here. That's the x value e. The y value there would be 1. So what's ln of e?
It's 1.
It's 1. So you're left with e minus e. What's e minus e?
It's 0.
0. So this entire thing is gone. 0. Let's look over here. What's ln of 1?
0.
0. 1 times 0 is a 0, so this thing is gone. So what's the final answer here? Final answer.
Minus 1.
Remember, there's a minus sign here.
So 1.
1. There we go. So what did we just find? We found the area of ln of x. Again, ln of x looks like that. Goes through 1, 0 here, comes from down here. And it kind of looks like a square root function from there. To the x value of e, and again, e is somewhere between 2 and 3. So let's say this is e. The area here, okay, you see this area? Is exactly 1. That's all we just found. Cool?
Mm-hmm.
Let's look at another example. Maybe we'll skip the course. Let's look at this one, because this one we can visualize. So this one's the third case here. What's the integral of 2 power x?
2x over ln of 2.
Yeah, 2x over ln of 2. Pretty simple. You have a 4 here, you have a 3 here. So this will be 2 power 4 over ln of 2 minus 2 power 3 over ln of 2. Remember, ln of 2 is a constant. That's not the thing that's going to change. This x is what changes. Upper bound minus lower bound, right? So this becomes 1 over ln 2, 16 minus 8, 8. So it becomes 8 divided by ln 2, which is some number. Let me see what it is. It's 11.54. So again, what did we just find? Very simple to visualize. We know what 2 power x looks like. It's an exponential function. The parent functions always goes through 1, 0 here. It's the other way around, 0, 1. The y value is 1. So from 3 to 4. At 3, the y value is 8. At 4, the y value is 16, right? Like this. So let's see what we just found. We found the area from here to here. We found this area. Cool.
Mm-hmm.
Now,
Yeah.
doing that by hand is not going to be, I mean, you can't get an exact answer by hand. This way is better. So that's what we did. Is this difficult?
No.
Okay, let's move on to something else. We don't need anything else here. So let's look at the derivative first to understand how to attack this question. What's the derivative of this? What would be y prime?
You bring the 5 down
Yep. Everything inside stays the same.
to the power of 4.
And then
And then you times it by 3.
times it by 3. What is this called? It has a name. Starts with a C. The chain rule. Okay?
Mm-hmm.
It's called the chain rule. When you attack a problem like this, you have to consider this aspect as well. So let's see if we can do this. So the integral of this, again, it's a polynomial function. It's going to have a power of what? What's going to be the power when you take the integral? Right now it's 5.
It's going to be
It's
6.
going to be 6, right? But now, if you were to take the integral of this, sorry, not the integral, the derivative of this, you would get 6 times 3x plus 4 to the power of 5 times 3. So you'd get an 18. So there would be an 18 here. But there's no 18 here. So what do we multiply this by to get rid of that 18? It'll be 1 over 18, okay? Just flip it upside down. You can multiply by any number. The goal here is to cancel out the 18, so you'd multiply it by 1 over 18. Like that, and it would disappear. So the final answer here would be 3x plus 4 to the power of 6 over 18 plus c. Did that make sense or no?
Why is it over 18?
Because when you take the integral, you get a power 6, right?
Mm-hmm.
Now think about this. When you take the derivative of this, you would get 6, 3x plus 4 to the power of 5, right?
Mm-hmm.
And the chain rule component times 3. So if you were to take the derivative of it by itself, you would get 18 times this. But in this question, there is no 18 here, okay?
Mm.
But we have an 18 here. So we need to multiply it by something to get rid of that 18,
Which is 1 over 18.
which is
Okay,
1
that
over
makes
8.
sense.
Then you'd be left with this. That's what they have there, okay?
Mm-hmm.
That's one way of thinking about it. But you'll see later as the problem becomes more complicated, that method is not going to work. There's another way to do this. And this works when you have a function within a function. If you look here, you have a linear function, and then there's a polynomial function of power 5 on the outside. What you can do is you can do a substitution. So usually the nomenclature, we use the letter U. Let U be the inner function. What's the inner function here?
3x plus 4.
3x plus 4. So we actually we write it like this: U equals 3x plus 4. Now this is the difficult part. What we're gonna do is we're gonna take the derivative of both sides. Now the derivative of U is just like the derivative of x. It's a 1. You agree with that?
Mm-hmm.
But now we have two different letters. We have a U here. We have an x here. We didn't have U in the beginning in the question itself. But now we've introduced an extra variable here. So when you take the derivative, you have to take it with respect to the variable you're talking about. So the derivative of U is a 1, but that is with respect to U, and that is what we call du. The derivative of 3x plus 4 is a 3, okay?
Mm-hmm.
But that is with respect to x, so we say 3x. So what this means is that du is equals to 3 dx, like that. Now let's see that interplay. How does that help us? So back into the question. Now we don't have 3x plus 4 anymore. We have a u. The power of u, well, this thing is u, so the power of u is still 5 times. We don't have dx anymore. We have du. So we need to replace the dx. If du is 3 times dx, what's dx by itself? Divide both sides by a 3, right?
Mm-hmm.
That'll be du divided by 3. Now 3x plus 4 is a u. Power 5 is unchanged. And dx is going to be du over 3, like that. Now if there's a constant, you can always pull that out of the integral. You don't even have to worry about it like this. So that 3, I'm going to pull it all the way out. What's the integral of u power 5? It's just like x power 5. What would be the
It's u to the power of 6.
Yeah,
Yeah.
over what?
Um, over 6.
Over 6. When you take the integral, it cancels out with the du when you do integrate it. Plus c, because this is an indefinite integral. Now look at this. 3 times 6 is an 18. u6. But we did not have an u in the question to begin with, so the final answer has to be in terms of the x. So in the very last step, we just replace u with what it is. So the final answer here would be u is 3x plus 4. Replace that u with it to the power 6 over 18 plus c. And you're done. This is called the u substitution method. We'll do a bunch more examples on this. Hopefully this made sense because the concept is the same. Again, here we don't have to do it because I'm going to show you both ways just so you can start seeing it that way. Because the inside function is linear, just like last time. If the inside function is linear, you can just kind of think about it in terms of, well, what do I multiply it by or divide it by to get rid of the chain rule component? But we'll see later that when the inside function is not linear, then you have to do the substitution. And I'm going to show you both ways. And remember this is the baseline. Cosine x, the integral is just sine x. There's a chain rule component, we just divided by that. So there's an a here, there'll be an ax here, we just divided by an a. So what's the integral of cosine of 4 theta? It's going to be sine of something. This is the formula.
Sine of 4 theta
Sine of 4 theta over anything?
over 4.
Right. And then you're going to plug in the bounds. And it's going to be the upper bound, so sine of 4 times pi over 8 over 4 minus the lower bound. 4 times 0 is a 0, sine of 0 is a 0, so the entire thing is a 0. Here this becomes pi over 2, sine of 90 or pi over 2 is a 1, so the entire answer is 1 over 4. And you're done with this. That's it. Not that difficult, right?
Mm-hmm.
Maybe we'll save the u substitution for a problem that we actually need. This one, you just do it this way, honestly, it's way easier. Yes, this one. Now you see here, there are 3 functions. You have the q on the inside, there's a radical there, so you have a square root, and then you also have a quadratic on the very outside. Now let's say there's no x squared, right? Let's just say it was just this. What is this? 1 over 2. Let's say the question was just this. The integral would be, do you agree?
Mm-hmm.
It's missing something. That's not accurate as it is right now. You see, because there would have been a chain rule component here. If we take the derivative of this, you see on the inside, you would have 3x squared, right? The derivative of this.
Mm-hmm.
But right now, we haven't accounted for this. So should it be 3x squared down here? But if you had a denominator here, when you take the derivative using quotient rule, you should have the denominator squared over here, right? So something's not right, which means the traditional way of just adding powers doesn't work for a question like this because of that chain rule component. So far it's worked because all the inner functions were linear. So we could just multiply or divide it by something, but it's not going to work for this one. So here we have to do a U substitution. You have two choices. You could either make this your U, or you could make this your U. Just the inner part, not this radical itself. Now, which one do you pick as U? Here's the trick. Whichever U you pick, if you take the derivative, like the derivative of here would be 2x, that doesn't really help me with x cubed. But now the derivative of this would be 3x squared. You see x squared, x squared. I can cancel them out. So to recap here, when you have multiple options to pick as U, you should pick the one where if you take the derivative, you get the other function that you're working with. So let's see what that looks like in play here. Again, we have to identify that this is going to be a U substitution question, because when you just take the integral or the chain rule component becomes a hassle. So we're going to say let U be x cubed plus 8. What's the derivative of U with respect to U?
It's du.
Yeah, what about on the right side?
It's 3 dx.
So it's
Or
gonna be, no, not 3 dx. There's a dx. Here's a 3. What's between them? X squared.
x squared.
And the derivative of 8 is a 0, so that goes away. So you have 3x squared dx. Cool? That's step number 1. Oh, actually, we need to replace dx. So I'm just going to say dx is du over 3x squared. And that's the first thing you do for any U substitution. Now, this one you'll notice is a definite integral. You see these bounds? They are in terms of x. What we're going to do is we're going to replace those bounds and make it in terms of U. Okay?
Mm-hmm.
So here's how it's going to work. For the lower bound x equals 1, we just replace this function here as 1. So when U is 1, sorry, not when U is 1. When x is 1, U is going to be 1 cubed plus 8, 9. So now look at this. X equals 1 becomes U equals 9. For the upper bound, when x equals 2, U becomes, again, I'm using this function, 2 cubed plus 8, 16. So the upper bound is 16. This x squared, we didn't touch it. I'm going to leave that as x squared. This radical, we didn't touch it. I'm going to leave that. What's the inside part of the radical? What did we replace this by? It's right here.
With U.
Yeah, with U. So now that entire thing is gone. That's a U. What about dx?
It's du over 3x squared.
Yeah, du over 3x squared. Like that. Now again, we have two variables here. We have u and x's, but look at this. Because we picked u as x cubed plus 8, this x squared and this x squared cancels out. And this 3 that's on the inside, that's just a constant. You can bring it all the way outside. So it becomes 1 over 3, u is 9 to 16. Again, I'm going to write it in this form so that it's going to be easier to take the integral. What's the integral of u to the 1 over 2? Remember, it's going to go up by 1, right? So it'll be u
So
to
with
the
3 over 2
3 over 2. What do we divide this by?
by 3 over 2.
Yeah, by 3 over 2, which is the same thing as saying multiply by 2 over 3. So I'm going to write it in this form. And then you have u equals 9 and u equals 16. So here you have 2 over 9 times 16 to the power of 3 over 2. Well, 16 is 4 squared, so I'm going to write it as 4 squared to the power of 3 over 2 minus 1 over 3 times 3 squared. 9 is 3 squared, so I'm replacing u with 3 squared times 3 over 2. This again becomes 2 over 9. So what's the final answer here? This goes away with this goes away with this. So it's 2 over 9, 64 minus 27. Whatever that is, 33, 37. So I think this, and that's going to be your final answer. This, you can just plug it in a calculator. But the most important part here is this. Well, it's this, the very first thing that you do. Because if you do it the other way around, I think you're going to be stuck. Let's say du, let's say you messed it up. You know what? Let's say you're like, hey, I'm not going to pick the inner part. I'm going to pick the outer part as my u. Let's see what would have happened there. So let's say u is x squared. Then du would be 2x times dx. So dx would be du over 2x. So when you go to plug it in here, let's ignore the bounds. You get u times x cubed plus 8 times du over 2x. Yeah, now here the issue is that this x, you cannot use that to cancel out with this x squared. This becomes a problem now because you're trying to integrate two different variables. You have u, but you also have x cubed. So that becomes multivariable. It becomes a lot more difficult. The way we did it, we were able to cancel out the x's straight up, the x squared, x squares. So that way is much easier. You only want to do it with respect to one variable, if possible. Let's try doing this one. Now again, you have a linear function at the bottom. You don't have to do a u substitution here. It's only when there are two functions here. One of them is 1 over x. This is the bigger picture. And the smaller picture, the inner function is a linear function. But because the inner function is linear, it's not a u substitution question. You could do it like that, but you don't have to. I'll show you both ways. Here's the first one. Here's the idea. If y is ln of x, y prime would be 1 over x. Here's another example. If y is ln of 5x plus 3, y prime would be 1 over 5x plus 3 times the chain rule component 5. So here, what's the integral of 2x plus 3? So we're down here. It's going to be ln, right, of what?
2x plus 3.
Okay. But if you were to take the derivative, you'd get a 2 on the outside. So we need to multiply this by something to get rid of that 2.
1 over 2.
Yes. Plus c, and you're done. That's it. Same thing here. So it's not as difficult as it looks because we can just do it really quickly. So if y is cosine, y prime would be negative sine. So the integral of sine x is negative cosine x. And then you have to account for the chain rule component. But again, the inner function is linear. What's the integral of 6 sine 3 theta? And the idea is sine becomes negative cosine.
So it's 6 negative cosine of 3.
We can put the negative sign on the outside as well. Yeah, so 6, negative 6, 3 theta. But now the chain rule. What do we multiply or divide this by? See if you were to take the derivative of this as it is, right? You would get negative 3 times 6 cosine 3 theta. 3 would come out, yeah?
Mm-hmm.
So you have this. Actually, you would have this. You'd have this. You need to multiply that with something so that the final product is just this. 6 cosine 3 theta. Sorry, not 6. I messed up the derivative. It should look like this. You have this, you need to multiply it by something so that the final product looks like this. What is that something? Well, it's 1 over 3. Negative 1 over 3, in fact. Okay?
Mm-hmm.
So you divide the final answer by negative 3. So you'd multiply this by negative 3. So here the answer would be 2 cosine 3 theta. And then you plug in the value, so you can do that on a calculator. And again, because the inner function is linear, you don't have to worry about the u substitution. Let's try this one. You'll see that there are 3 functions at play here. You have e power x, you have this linear function on the outside, you have the quadratic on the inside. Do we do a u substitution here?
We do.
So what's u? You only have two choices really. Either your u is this or your u is this.
It's the second one.
So let's say u is, you can put the negative as well. What would be du?
It's negative 2t.
Times what? Remember the variable, you have to specify what variable you're talking about. So on the left we have u, on the right we have
dt.
dt. Yes. So that means dt is going to be du over negative 2t. Like that. It's part one. Part two is also the bounds. Right? So if t is 0, u would be negative 0 squared, 0. Do you agree?
Mm-hmm.
What about when t is infinity? What's u gonna be? Replace t with infinity here.
It's just infinity.
So it'll be negative infinity squared, right?
Mm-hmm.
Which is weird. The negative doesn't apply to the square sign, so infinity squared for some reason is still infinity, so it would be negative infinity. Okay?
Mm-hmm.
Negative infinity. Now we can replace everything. So u equals 0, negative infinity. T, we didn't touch that t. E to the u times du over negative 2t. All right, what's the first step? Notice we have two variables. We don't really want two variables. We want to kill the t's if possible. See, there's a t here. T here.
Mm-hmm.
Gone. See you later. Minus 2, we can pull it out. You don't have to, but I like keeping it clean inside the integral. So now we have e to the power of u du. Remember, e power x, the derivative, the integral, and the derivative is itself. So what's the integral of e power u?
It's itself.
Yeah, it's itself. So you have e power u. Um, there's one thing that I am missing is that, let's see what we get. What I'm thinking is that this should always be your lower bound. This should always be your upper bound. That's how it was in the question, but when we did the substitution, the bounds have flipped actually. So I'm going to replace these two. The lower value should always be the lower bound. So here our lower bound is negative infinity. Our upper bound is u equals 0. You always follow the number line, right? So negative infinity is here, so that should be your lower bound. This is your upper bound. Any number on the right is going to be the upper. So let's do it like this. So here, what do we get? We get 1 over minus 2 times e to the power of 0 minus 1 over negative 2 times e to the power of negative infinity. What is e power 0?
1.
So the answer here is negative 1 over 2. Now, e to the power of negative infinity, we talked about this before. That is the same thing as 1 over e power infinity, right? And e power infinity is 1 over a very large number, so it's 1 over infinity. So the entire thing is a 0. So because e power infinity is a 0, this entire thing is going to be a 0. And that's going to be your final answer. Cool?
Mm-hmm.
So this one was an EU substitution question. It's not terribly difficult. You just have to make sure you do it with the right one. Because over here, if you did it with T, yeah, you would be stuck. You'd get into the same problem we had last time, where you would have two different variables here with no way to cancel them out. So that is doable. We'll get into it maybe in a couple of weeks. All right, let's call it there for today.
Okay, thank you.
See ya.